our presentation on real-time object algorithms. So you've probably heard of things like YOLO, RCNNs, and things like that. And just want to give an overview of what these algorithms are, so that when we decide, to apply them might be a good idea. So when you read the papers, there's this historical aspects of how it was developed, and it's kind of unclear. So just go over those things. So and yeah, if you have some points, just feel free to raise your hand and just start talking about it. Because if you have any confusion, just ask questions. Okay. So let's start with the if you've taken the Udacity vehicle detection and tracking, we've done something similar. Like, how do we detect objects? So you still remember we had these things called hogs and color histogram. They had all these features, and those features would detect if a car was in an image or not. So yes or a no. So it would classify yes or no. And then what we did was we'd make all these small boxes, and we'd say yes, no, yes, no, yes, no, in different resolutions. Some these are bigger, some are smaller. And then we'd have this voting system, and then the highest votes would be like, okay, this is probably what the car is. Let's start off with that. And there's no deep learning involved in any of this, right? These are just like hogs and color histograms. If you take a term one, you'd have to do term one the last project. So we do, but there's it's things have moved on from these things. Let's discuss more on this. Okay. So with convolution, we also do convolutional neural networks on the Udacity course. So, but we only do one thing. We just do the classification. So let's run all the things that you can do with CNNs.
Victor, can move back just a bit.
What?
If you don't mind.
What is that? Oh, the camera.
Yeah.
I want to know.
Okay. So
sorry.
So this is the one that we so is there a cat or is there not a cat? So you have the convolution neural network, and you have maybe two cat or not cat thing at the top. You would say yes or no, able to do some values. But so what else can you do with a convolution neural network? You can do something called localization. If you know there's a cat, you can ask it, where's the cat? You train the model to be, you'd have to have label images with where the bounding box for it is. And that's called localization. And so there's object detection. So you give it an image and you're like, there's a dog and there's a cat and a dog. The difference between localization and object detection is localization, there's only one or two, or you have to specify how many. But with object detection, it can have as many as you want. So here's three. They can be multiple. So there can be two dogs and one cat. But if you're doing some sort of localization, so we'll go a little bit more into it. And then there's the image segmentation, right? So instead of putting a box around it, you actually have a Photoshop style contours, a selection, so you know exactly which pixel the cat and the dog occupies. Okay, so these are the things that you can do with convolutional neural networks. Okay, so let's look a little bit at localization. So before it's you only have these classification class scores. You have an output of a probability output of if it's a cat or not, right? So how do you also do localization? So you ask the CNN, is there a cat in the picture or not? You say yes or no, where is the cat at? So very simple, you have a regression head. So along with the classification, you put a regression head, and it will output four values. So the coordinates of the box. And you'll have to train your neural network, but it will also produce, along with if the cat is there or not, the box in which the cat occupies. So it's called, in the literature, it's called localization, and then they also call it regression. It's regression because there's an actual number being outputted for the box, not just yes or no or a probability value, but an actual the actual box. Okay, so that's called localization. So some of the older how do you we know how to do localization. Like let's kind of use it for object detection. So some overfeed, the overfeed algorithm was, so you have an image, and then you divide it into 4 sub-images, and then you do localization on each of them.
So when you say localization, that
It gives you the box.
within what you're localizing, just within the screen?
Oh,
or
just this one, so this part. So it's just
what
the
is
one.
it like being localized relative to?
No, that's not. Localization just means, so that's you have to be careful of that.
Right.
It just means it gives you a box where it is. So yeah, so classification means is this a cat or not a cat, or like as many labels as you want, classes of labels. Localization means here's where the cat is.
So within, so
Where
you see
is
an
the
image
object
basically,
within the
yeah, and so relative to the screen or the frame of the of the image of the camera, where that image is.
Yeah,
is
the
localized,
cat is
like-
so, yeah, this one like it will give you the coordinates of the box.
So it's pixelating in pixels.
Yeah, big in pixels. Yeah. Yeah, so that's localization. But so if you wanted to do more, you could combine them together. So you could do localization on each subset of it, and then you could combine them all together into a bigger one. So that's like the overfeed algorithm, and that was one of the winners. So the okay, so let's move on. The problem with that is you have just four regions, right? So you could say, okay, but it could be in any of those regions, how do I even know what you're gonna, like you just divide it into 4 pieces. What if you divide it into, what if there's exponentially growing number of regions that you can look at it in an image? So how do you even start off? Did you just look at everything like we did in the project, or is there something better? So we came up with something called region proposals. What happens is you give your CNN a region, and we'll say, is there a cat in there or not? And localize it within that region. So these algorithms are called region proposals, and so one of the region proposal algorithms is called a selective search region. So it's like the old computer vision style. You select pixels if they're close, look close together. You merge them, and then you have these big regions. Together. Okay, so there's these algorithms that you can do that, and it's not. This doesn't involve deep learning. So our CNN. So the algorithm is basically get some external.
What can you just say? Our CNN stands for.
Region CNN.
So
CNN
region.
News.
The CNN means
Yeah.
convolution neural network. R means
Oh,
region.
oh.
I don't think it stands for anything.
Right.
What was the other, before this, the classification was done not using neural net, it was using
Oh, the first one, the
other
one.
stuff you're talking about? Yeah.
Oh, this was from the project. Yeah.
Yeah, so the one after that? Yeah, like this convolution and pooling and the final convolution feature map. All this is not using neural nets.
This one is using neural nets. So it is using. So when we make CNNs, we have the classification, right? So you will just output a cat or a cat dog, whatever classes, and then you can also get localization by just adding this thing.
Okay.
Just gives you like the box coordinates, like x, y, width, height, or something like that, or x, y, x1, x2. Just gives you these 4 numbers, along with if it's a cat or not a cat.
They're all convolutional neural networks. It's just a question of which
Yeah.
flavor, if you will.
Yeah, or how you like put things in the end. What you got.
Mhm.
They're all convolutional. These things are all convolutional, and you basically use the ones that have won the contest, like
Even the
ResNet.
first one, yes, no, is it a cat or not?
Yeah,
Still, yeah,
use
okay, yeah.
use something like ResNet or the competition winners winning ones, and they're all interchangeable. Any image classification algorithm, CNN, you can swap it out for one or the other. So some are better, some take more resources, some, so you can just swap all of them.
What about that first slide that showed the, what was that, infrared image or in that first slide?
Oh, that's from
What about that?
that's from the Udacity.
It's a heat map.
I mean the bottom two images, what are those?
It's a heat map, so
Oh, heat? So infrared?
So, well, no, it's like how much overlap of all those boxes up there. You kind of, each box has like one vote. So if there's multiple overlaps, you'll get higher and higher numbers of, count. So that it'll show up brighter in the heat
Oh,
map.
okay.
Heat map is just a generic term. It's not like actually measuring heat.
Okay.
but there's no heat. Right?
It
Yeah.
looks like it's showing.
Yeah.
It just you just have the RGB, the R value on the floor,
Okay.
or something like that. Okay, but okay, region proposal and RCN. So, so you just take some sort of region proposal, do the convolution on it, and say is it there or not. And you do localization also if the boxes are kind of not very good, then you can move around a little bit. And yeah, so I mean this works pretty well. So, but the problem with this one is it's really, really slow. You have a lot of regions, right? So, and then you have to go outside and use another algorithm to generate your regions and then test them. So, okay, so bounding box regression. So one of the things.
Pizza Man's here. Hi, thank you so much. Awesome, man.
Yeah.
Oh, sorry, go ahead. Forget about those guys.
Okay, so so one of the
Pizza party.
You wanna?
You can sit on my chair there.
We're gonna sit right there.
do you want to take a break, Alex, or?
No,
Keep going.
I think I've done the 10 minutes or so. There's that many slides left. There's a slide counter. So, but anyway,
Yeah.
so
So Mike,
from the given proposal, the boxes for proposals, you use regression to fix it. If it's if it's too far to the left, too far to the right, you can kind of fix it. Like kind of get big or small. So
What regression outputs? Which ones?
the regression from the localization. It's like the sorry, the terms are slightly confusing. So. So localization is also called regression because it produces four output points, x, y,
Yes,
z.
the X, Y, and
Yeah.
yeah, okay.
So it's called regression because it's producing numbers
Okay.
instead of classification. This term is used, so it's called regression. So these regression outputs, I could have said localization outputs, I guess. But localization output, it will say, oh, this is a good proposal. It's like the cat's way too, I'll give you a different proposal rather than, so the localization of the regression will fix some of those. Okay. Okay, so it was really slow, so they came up with a new one called fast RCNN. So you extract the features from, so it was like, why do we have to take the image and sort of be outside and do the regions and then feed it in? Why not just get the regions from the, from the features from the convolutional neural network? So CNN features, let's just use that to create the regions of interest. So we don't have to go outside and have, and store all these data and do that. So this uses just, the CNN features, right here called the feature map, to create the regions of interest, and then you do image classification and localization on it. So this really speeds up the system. So we call it fast RCNN.
What features is it driving off of to define the regions of interest?
So-
What features are coming out of that CNN? to
Yeah,
define-
so you have so there's an algorithm for it. So when you do that, things are slightly modified, right? because
Okay.
you've gone through the networks, but you'll have to have a modified algorithm. But it would be similar. It would just figure out these looks clumped together, and then you also have, yeah, okay. So then they came up with something called faster CNN, because it was like, wait, why are we relying on some external program to give us the region proposals? The neural network is a learning system. Why not learn the regions as well? So it could give you the regions as well as the whole. You could do the whole thing. So so there's a whole network for it, and then they created a region proposal network. So that you give it, you give it the images, all the regions that it has, classifications, and once it's trained, it will actually propose new regions, and then these regions will go and you do classification and regression and bounding box regression, all that stuff. So it ends up with four loss functions you have to work with, but everything is one neural network, and it's a lot faster. So it goes down to 0.2 seconds to process a picture.
0.2 seconds.
Yeah, on a like the GPU. Yeah. So I mean, this is relative. It's not going to be on a CPU. It's on a like relatively deep GPU, but
Does that still seem kind of slow?
it's still slow. But yeah, you can't. It's 5 frames per second, so you can't do real time.
Yeah. Okay.
So there's more algorithms. Okay, so this is, but this is the one that won the contest last year. This algorithm. So they have yearly they have a contest of who can classify and localize the best. Even though this is slow, it's just it's the best one, gives you the best results. Okay, but you can sacrifice some of the accuracy for speed. So this algorithm is called YOLO. You only look once. So the idea here is, so what you do is, you say instead of like having somebody else like propose regions, like here are the regions, here you should look into this and this. Fix the number of regions. Boom, you divide your image into S by S grid. It's fixed, and each grid gets 3 or 4 overlying scales on them, so it looks something like this. But then you do localization and regression on it. So one of the cool things about the localization is that the localization, this localization box, will actually give you a bigger box that's even outside of the image. So if you get this part of the bicycle, it says, yeah, I know this is the bottom part of the bicycle. I can sort of like, yeah, the whole bicycle must be much bigger. Even though I don't have the size, it will give you the entire size. So you have all these voting. So even though this one says, oh, I'm a bicycle, but then it will say, yeah, the bicycle is probably this big, And so with this, here's the
Question.
oh, sorry.
What if the real bicycle in the picture is like sewn in half, and there's no other half of the bicycle?
So what will happen is basically we'll think there's the rest of the bicycle. It will still project.
How would you train for that? Like, this is a bicycle, this is half a bicycle.
No, you still train for the whole bicycle, but then it might be obscured, right? This might be a big dog and you can't see the bicycle behind it. But it will still say, yeah, the bicycle is still there, even though you don't see it, because it knows what a bicycle looks like.
Well, I'd say unicycle at that point, right?
Oh, unicycle, the handlebars.
Classification.
Yeah, but so also the thing to remember is in the classification, you are limited to the classes you can't. It's not going to just predict everything. So if you have bicycle and unicycle, then you better have enough samples for it. You can't just predict anything. You're limited to the number of classes you can predict to. I mean, it could be thousands, but it's not general purpose. But yeah, so the trick here is that for every such block, it generates the size of the box and the accuracy that the localization and the accuracy of it. And so you can do, and then each one has a multiple sets of boxes it starts out with, and then so you have a voting system. And so what happens is the output is always fixed. This is the only number of only number of regions that will ever check. So it will not check. So in that way, it's limited because it can't get. In that way, it loses some of the accuracy because there's only so many boxes you can check. Whereas RCNN can check anything, but it's super fast.
And it's deterministic
Yeah.
in the sense that,
Well, all of them are deterministic, but yeah. It's,
yeah, in the sense that like the running time would be the same regardless of how many objects are in the same.
Yeah. Yeah. Okay. So and then there's a slightly modified versions of these things called the SST, the single shot detector. So instead of what YOLO does, it just breaks it up into one. So it also does something like instead of breaking into 8x8 and also does a 4x4. So it does it in two different aspect scales. So it's a little bit small advancements to the idea of YOLO, of just like cutting an image. It just does an S by S grid, but it has multiple ones. So S by S grid, and then S by 2 by S by 2. So it also has these higher resolution coding system that you have, and then so it's a little bit more accurate than YOLO with these. But the YOLO version 2 also has these added to it, so that it's always in constant development. Okay, so these are this is close to the state of the art right now with real-time object detection, SSD, YOLO, and maybe YOLO version 2 is the one you'd use if you wanted to do the general object detection. If you just want to do localization, if you're just looking for a stop sign and there's only one, then maybe just localization, you just beat all of it because you don't have to worry about regions or anything. You just like stop sign or no stop sign, where is it? So, but if you want to worry about all the different cars and all the different signs, all the different things, then you'd have to use a sort of like a full-blown object detection to it. Okay. And so just if you read papers, then they just a few things, the unit of how good your algorithm is measured in MEAP. So if it's 0, then it's bad. If it's 100, it's good. I think the best ones are around 60 something. It's pretty good. Well, I mean, it's just a scale. It doesn't really mean anything. So, but it's the anyway, it's the area under the curve of precision we call blah.
But a human would do like 100%, right? Most of the time.
Not as fast though.
Yeah.
I'd rather, yeah.
I don't know how fast humans would do
Would
it.
it be like over 90%? Otherwise, you wouldn't be able to recognize a bicycle land 1 out of 10 times. Is that the idea?
Yeah, I don't
It's
know.
actually
Yeah, that's
pretty far away from the human.
I think it also takes into account the area you propose. So if your area is off by some 1 centimeter in the image, so maybe your score is low, but you still detect the bicycle. But the area is not exact. So that's why the number is generally low if you compare with the regular image classification. So the regular image classification can be like 99.4% if you are just comparing what the object is.
Right.
But the task is to also predict where the image is, like the boundary of the image.
That
So
becomes a more
that
difficult-
becomes a bit difficult. I mean, you use it predict it, but it will not be exact in that box. It might be off by some pixels. So your score will be low in that case. That you missed a few pixels in.
Okay.
But
So
you still have the
performance is deeper than just this one score. It's also like how big the error is.
Yeah.
Okay.
So on the classification, it's pretty straightforward, right? Like you detect all the things in there, and in some cases, the classification is better than human, because humans will make mistakes, or they will call it weird things. So, but yeah, I mean, it's another weird thing is like a person will never mistake a goat for a dog, but a computer can. So there's that whole that whole thing about humans and all that is it's okay, but anyway, so I don't know if humans are hundreds. They probably are. If it's perfect system, it's probably 100. Okay, and so if you look at there's these data sets that are widely used. The Pascal VOC is the 2010 one. It's pretty small, and then ImageNet detection is another one they talk a lot about, and it has one object per image. So it's just mostly for localization. The MS Coco one has multiple objects, so if you want to like, but this one is really huge, and if you want to test your, or train your, these are fully annotated data sets. If you want to build your own, then you use these. And then they, in papers, they always compare the performance to these. So if you see these, then that's what they mean, the Pascal VOC of MS Coco.
How big are they? Like the order of magnitude, like 10, 100, 1,000, 10,000?
Yeah, it's half a million. I think this is 80,000 or something like that. This is also like 100,000. But they're fully annotated, so that's the boxes are drawn and because the image is one, but the value is in the human annotation, right? So
yeah,
and you need that to train your system.
So I actually asked a question, like when you do a capture right now, you label the cars or label the street signs. Do you think they're building a data set internally?
I think there are some test cases. So it will ask you sometimes twice, or maybe some parts of it's not trained yet. So they are collecting data on there.
So the idea is they're going to take that and they're going to use it and they're going to create their own data set.
Yeah, it's already using. Used by Google. So.
Oh yeah, of course.
Google.
Yeah.
Google.
I think it's more of a test than learning, though.
I mean, it's combination of both. So they have certain percentage which is for learning, and some for actually.
If it was machines doing it, and say a human will score 95%, but a machine will score 90%, and all the time computer is getting 90, the algorithm won't be able to determine between a computer and a machine. I think that's used as a test. Are you a robot or not? I don't know if they're actually there's backwards propagation to where they're actually adjusting their algorithm based on the answers that people have.
You're
given.
saying that they might.
No, but they are.
I don't know if they are.
They are getting data and annotated on some image. So sometimes this is wrong, and click next, it will give you another set of image. Sometimes it can go on 3 levels. So one of that can be a test for them to get the data for them. Because they are not actually checking it.
Yeah, they have the ability. They have like Google Maps personal street. Yeah. So imagine that they start using that.
And so there's the link. So I'll connect the PowerPoint to slides to check it. So these implementation of SSDs, you can go try and play around with today. Most of my object detection class videos from the Stanford CS. It's really great videos explaining. It goes into more detail, to what I've gone to, and there's some more. If you want to read more about these SSD. So okay, so I forgot about. Go ahead.
So image detection, but in images is there's like seconds.
So that's YOLO, and it's 60 frames per second easily.
Okay, 60 frames a second.
Yeah, so so that's 60, and then but you need a GPU.
But do you think that the cutting edge research now is not maybe so much in image detection, but also using a fact, because when you take an image, you're removing all the information that you've had previously about the history of the previous past second. This maybe not as applicable as using it in video, or using previous information about, I thought it was in this top left a second ago.
Yeah.
I think I'm going to spend
so
more
especially
time.
like a tracking something, right?
Yeah. Is that a difference? Study, or is this?
I think so people are trying to integrate that into this, but right now this is purely taken as an image detection problem. But yeah, if you want to apply it on an image, there are previous techniques which we can use to track what it found in the previous image and what in the next. But I've never seen any implementation.
Okay, interesting.
Yeah, so I didn't mention detection or tracking, right? So that's there's no contest for that. There's no annotated data for it. So all the annotated data is for images. Maybe there is, but there's no big contest. I haven't heard of any of those. And so what we do is basically use them for each frame, the same thing. probably use the previous one for picking the next ones.
So the 60 frames per second, that's only for boundary boxes. That's not for the actual outline. The actual outlines, they run at like 5 to 7 frames per second, correct? Max.
So the outline is, I don't know, it is a lot harder problem.
Yeah, so like 10 times slower. But you could literally just have 10 GPUs in your car, right? They don't weigh that much. And you could have one, okay, I'm doing this segment, I'm doing this segment, and you combine all of them and you have your 60 frames per second. I mean, it's going to be thousands of dollars worth of equipment, but still, you could, right?
Yeah, you could.
Does the problem become a lot harder when you have when it's in 3D? Like, you know, we were talking images, but it becomes
Like stereo.
yeah, or like
And
LiDAR
much.
data.
Yes, double the amount.
So,
And sometimes
For LiDAR,
reconciling all of them, absolutely.
they have something called voxel net. So it uses the pixels or whatever the data points you get, and the bounding box is a 3D shape compared to a 2D thing. So Apple has released the paper, I think, last month on voxel net. So they use the LiDAR data. It's basically a 3D data of the world in front of you, and you are trying to classify like which volume is what object. Is it a pedestrian? Is it a car? Or is it something else? So they are basically using 3D data points to 3D objects in there.
Also, the beautiful thing about neural network is you could literally fit in 100 cameras in it, and it'll just figure out how they relate to each other. It's going to be running slow, but it will figure it out eventually.
But you'll have to annotate it. So that's
Yes, if you annotate it correctly, but then it'll actually figure out, okay, this camera must be mounted here in this car, here. It will learn it, and you don't really have to do much more engineering than just augment your data set.
So I have another question. Sure. So one concern I've always had with neural nets is that the explainability of them and the debuggability and correcting them is pretty difficult. So I don't know like what like the opposite case would be where you would maybe it caused a crash, like your algorithm literally caused a crash, and you want to go back and make sure that this specific instance gets excluded. How would you like change these algorithms to exclude specific cases or corner cases? And does it become like this kind of crazy thing where you start doing more if statements kind of?
Oh, no, no, I mean, for perception, for these perceptions, you know there's going to be errors. I mean, even a few pixels can completely flip on what it thinks the class is. So there's no way around it. There's, it's going to have errors, and so it has to be dealt with somewhere else. Oh, sorry. It's going to have errors. And that's just part of people. It's not going to be perfect yet.
It's a black box.
Yeah, it's a black box. So the answer is
It's kind of like opening Emotion's brain right now and seeing how it works. It's difficult. The weights are in different places for different people. There are some
I'll make
visualization
mistakes
techniques out there that'll show you kind of similar to heat map. These are the features that I saw, but they're not perfect.
I mean, there's work on explainability on why it did something. You know, there's that huge problem, right? You can change a few pixels and you'll completely think it's a different class.
Yeah.
And so hackers could just like, or just put something in the back of your car and it doesn't think it's there.
That's an active area of research right now. In fact, there's research papers out there right now that hackers or researchers really have taken on adversarial type roles and trying to like convince like a picture that looks like a bus actually looks like a cucumber or something to the algorithms, and like visually, like if we were looking at it, we were like, that looks nothing like a cucumber. It's just like they can change the pixel values of like the JPEG encoding to make it look that much different to the computer that's just seeing it as ones and zeros. That they could. It's really ridiculous, and like visually we can't tell the difference.
Yeah.
We definitely think that's a bus.
And there's no easy way for you to fix that. If your boss was like, I need you to fix this by Friday, and you have no way.
You're just like, I gotta retrain it.
No, even retraining.
No, this actually happens in animals too, like cats. If you put a cucumber in front of them, a lot of cats think it's a snake and freak out.
Yeah, that's true.
You can find a lot of videos online. Cats and cucumbers. Like you put one behind, it kind of turns around and like jump away. It's the same thing. Like it can happen to humans too. Like that's why you get frightened. Like you didn't expect someone to like see them like I'm freaking scared. So that happens to all neural nets. I feel like specifications.
So maybe part of the approach is using accepting the fact that there's unreliability and things like this, and then using redundancy and different types of sensors trained on the same area, and then taking some kind of fusion of those results.
Yeah.
Is that the path forward, I guess?
I mean, there are at least 5 to 7 sensors for redundancy.
Yeah.
Really?
Yeah, I mean, like radar, lidar, and ultrasonics.
Trained on the same.
Image. I mean, to see that if there are any objects nearby, or if
And some of them, yeah, they work together. Like
I
they
think
use all the data, so maybe some, and then they have to be redundancy, right? If one sensor sees it, what if it's not really there? But then if you get it from multiple, then
I think sensor fusion is like more
statistics. It's a game of statistics.
It's a more active area of study for the next phase.
Yeah, I mean,
of,
yeah.
so you need to make make sense of all the data, like what.
What you could also do is you could take this one black box and break it up into like 10 black boxes and connect them between with code and actual visualization, saying, okay, these were my objects here. This is why I made this decision. But it's going to slow down your code.
Yeah. Okay.
Also, another great example of useful applications on YouTube videos. If you ever seen someone driving in a car and their passenger's asleep, and there's like a semi truck being towed, but it's facing toward you, they'll like wake them up with like screaming, and the passenger will think the semi truck is coming at them, and they'll just freak the fuck out because then you specify, you know, the information.
Yeah.
So I feel like it's always going to happen. You're never going to have 100%.
Interesting.
Because it's more of like the snap judgment, right? Like you taking one single frame or like two, like with some motion, and you just don't have enough information yet.
Yeah.
Or if you look at something for 5 seconds, you know, okay, that's a bus, not a cucumber.
Yeah.
Or cucumber, not a snake.
Yeah. Do you think that there's ability? So you talked about your CNN being able to, you know, output different corners of that box. Do you think you could also output depth from an image? Like,
yeah,
I think this cat is 3 meters away. I think
yes, absolutely. Absolutely, because you know that normal car is this size, and here I see it's taking up 10 pixels, so it must be far.
I mean, you can output as long as you have annotated data.
Somebody's got to go through it.
If you had LiDAR data to go along
That's
with
actually
it, you
really
could
good
have
point.
it as an input.
You could actually create your own data set.
Yeah.
Yeah.
No, like while autonomous cars will be driving, they will be collecting more data, and they'll be learning themselves. The beauty of a neural network is that you don't really freeze it. You can freeze it if you want to, but if you just let it keep on learning, it'll get better and better over time, just by doing what it does, and you're gonna have virtually no accidents. And if it does have an accident, it'll drastically change itself, and like it'll probably never happen again. Where humans, every single human has to make the same mistake in the road. Where here, if one car made it, you know, a mistake, that would, like, the rest of them will probably update to the same patch. Okay, this is how you not hit the street goal, you know, something like that. Interesting. Pizza time.
Okay.
One thing. How does that relate to what we're doing?
Yeah.
No,
Yeah.
Oh, come on. It's pizza time.
Yeah.
Yeah. Are we making a cat detector? Is that
Yeah, the difficult question.
So what we'll have to do is we have to do. So one of the things is we have to detect stop signs. So when we see a stop sign, we have to stop, or any other road signs or street lights, traffic lights, and other obstacles in the course. So if we're driving this car and there's other obstacles, it has to like, okay, there's an obstacle, I need to get to the next lane or avoid it. So that's one thing. And then if there's a stop sign or any other things that will slow you down or change things, then those have to be. So your RC car, if it has to drive autonomously, will have to respond to obstacles in the the street signs. Yeah, and I guess you could use ultrasonic and all those things, but they will all supplement together. Like, okay, this is a car, I should go around it, and things like that. Maybe you can detect roads, the paths, the lanes, who knows? So it'll be something we'll have to look more into.
Yeah, and that's why we're looking. So there's the TX2 that Motion has, but then also we use Raspberry Pi and the Video stick. That's where it might come in.
Okay.
So we'd like to test that because it's just a simpler and cheaper solution. And now you are no longer tied to a large board. You can have the computing capacity with you on the go and your keychain.
So we'll try different things and see what works. And especially if it's going to drive autonomously or goes through a racetrack, we'll probably have some sort of event, right? So
Yeah. But
race-
even these algorithms, I mean, theoretically, you could do that to a car.
Yeah.
Next, wirelessly, but sometimes,
You don't
You
want to
can-
go wireless. You don't
Right.
want your
but
shitty
imagine if
Wi-Fi
you can expand
connection.
your car's ability by just plugging in like a USB stick real quick, like anybody, you no longer have to be a technician to remove a module, replace it. You just, now we're kind of doing it with the OBE port already, but
So
not
when
quite
you're
to
when you're
that level.
training your algorithm, your hardware is like, is it more intensive than the actual
Yeah.
classification situation?
because you have to do something called back propagation. So you have to go forward, all the errors you made, you have to go back, try to fix those errors. You know, keep going back and forth.
So is the Jetson TX2 like, is that overkill for the fact that you just
No,
want
no. When you're doing the classification, you go one way, but you have to go through a lot of. There's a lot of data. The models are huge.
But you don't like when you're actually executing the algorithm,
You're
and
not training. Yeah.
so you don't need the Jetson TX2.
You do need it
still
because
need it?
yeah, because the CPU is not fast enough to be able to do it in real time.
Oh no, to train you don't have to do it in real time. You could literally run it on like
Yeah.
1995 computer. It'll take you 10 years, and then you run it on a modern GPU, and it'll still
But
work.
you still need the GPU base to actually perform the algorithm to do the classification
In real time,
in real time.
yeah. But
You
to
don't-
train it, you can be really
Yeah.
slow. It doesn't matter.
Doesn't matter. And yeah, but in order to do it in real time, that's the whole point. It's like you're able to do it. It's not on a server where you're just processing data. You have to get it done within a certain amount of time. So that's why the GPU is there. Also, like if you're doing research and you don't want to sit there for a long time, you want the results to show up in a day rather than a week. You know?
Mhm.
So you can train one, come back next day, and like, oh, see how it went. Rather than like, oh, next week. Then
And you can actually train in the cloud and run on a local machine.
Right.
you download the model, or most of the time you just download the model from Resnet or something. That is one of the competition, and then you modify it a little bit to suit your needs. Instead of looking for cats, you can look for stop signs by changing some of the parameters of it, and then you can text stop signs and something else rather than cats, because hopefully there'll be no cats in our RC car course.
No, we're gonna make a cat follower.
California.
That's the like a car just follows a cat. all the
So
time.
if you wanted to do that, then you do the cat thing also. Since all the numbers are
That's good stuff.
Bring it out, Alex.
yeah.
We're not going in that corner, that deep corner.